Nomi is a senior executive at Advance, where her mission is to seek out, identify, and invest in companies that help diversify and grow that Advance portfolio. Of course, you can find a full bio of Nomi on the conference webpage. So Nomi, over to you.
Thank you so much, Keith. And let me first just thank in addition to thanking you, thanking so many of our colleagues and somebody that we're all a big fan of here, Dell Hatfield, for inviting me to join you today. I think so much of my interest in technology is because of learning from Dell during some of the early years of my career. And I'm really forever grateful to him for his crisp explanations and thoughtful questions. So let me start by welcoming my incredible panelists. I'll start with Mariam Sorond. I'm going to just say a few brief words about each panelist. And again, the full bios are in our materials. Mariam joins us today from CableLabs, where she's Senior Vice President and Chief Research and Development Officer, involved with execution and adoption of new technologies for CableLabs members and the cable industry. I also want to welcome Dr. Don Chapin, who has a new role at NSF, a dual role where he's Special Advisor for Spectrum, a role in which he serves as Program Officer in the Electromagnetic Spectrum Unit in the Division of Astronomical Sciences, and also he's an advisor on strategic spectrum issues to NSF leadership. And next, Petri Mähönen, Professor and Head of Institute, the Institute for Network Systems of RWTH Aachen University in Germany. And Jonathan Ashdown, whom I've learned lives right down the road from me. I'm here in Syracuse, New York. Jonathan's in Rome, New York, where he is a Senior Electronics Engineer and Information Directorate at the Air Force Research Laboratory. Thank you to my panelists. I'm so glad you're all here with me today. So we're going to talk today about frontiers in the coexistence of engineering and spectrum sharing from a standpoint of in particular of discussing, we're going to discuss sharing across service boundaries. And I think it's important that we maybe start off with technology descriptions as to how we should define spectrum sharing. So I'll actually toss this out to any of the panelists to begin with, just if you could share some thoughts on how you define spectrum sharing, and probably just because we've been tasked with it specifically, spectrum sharing across service boundaries.
Well, okay, I'll get started. John Chapin here. So nice to speak to everyone. I just need to say that everything I'm saying is on behalf of myself and not on behalf of, does not represent NSF or the government's position. So I think we should use a definition that tries to capture the general meaning of the word as it's been used by the technical community over the last 20 years. And to me, what that means is spectrum sharing is the operation of independent systems close enough together that dynamic mechanisms are required to prevent interference. Independent systems are those that are controlled by entities that are distinct from the perspective of the regulator. So really, I'm focusing operationally on the use of these dynamic mechanisms as distinct from the more traditional static separation in frequency, space, or time.
I could weigh in also. So I think, you know, if we wanted to step back, it is very hard and there is no single definition of spectrum sharing. It really depends on the context and the parties involved in the discussion. And that's where it drives a different definition. You know, currently you can claim spectrum is being shared one way or the other, whether it's through partitioning it, a technology, a database, or regulation, right? This means that we really need to clarify which part of this are we talking about, and that's going to be hard in every conversation. Are we talking about two different regulatory bodies that allow different operations in the same band, or two different licensees using unlicensed and licensed spectrum? Or are we talking about two different technologies using, you know, the same spectrum? It's like, you know, I may call it turquoise blue and someone else may call it green, really. But I think one thing that perhaps we can agree on and talk about is that one of the most complex sharing scenarios is the sharing between government and commercial entities whose spectrum are regulated by different agencies.
Yeah, and from my perspective, I share a similar perspective. It's, obviously very complicated when you talk about spectrum sharing, even within, homogeneous body, such as the DoD, but you have all the various intricacies of, the various service, whether you're talking Air Force, Army, Navy, Marine Corps, Coast Guard, et cetera, and all their different mission sets, right? But if they're geographically co-located, currently, there are different systems that each service has to manage spectrum, and that utilization of spectrum really needs to, and the DoD is moving in this direction to be able to, share assignments across the services. But it gets even more complicated, as was just mentioned, when you're dealing with DoD or federal and commercial spectrum sharing. Because of not only a heterogeneous set of spectrum-dependent systems, but also a heterogeneous web of authorities that manage the utilization of those spectrum-dependent systems. So, I think that's why we're here today to discuss it. But I agree. One other thing I wanted to mention was that, if you look at the FCC table of allocations, you see a highly suboptimal solution to spectrum sharing. It's kind of like a static frequency assignment type of approach, very Marconian in nature. First transatlantic telegraph in the late 1800s, where a certain spectrum dependent system was allocated a certain frequency band, and ad infinitum. We don't really take the amount of time that maybe a certain spectrum dependent system needs to do its thing, or maybe it's a temporary license, but we need to think about how to be smarter about solving this multi-objective optimization problem in a more optimal way, rather than the suboptimal solutions that currently exist, where in large cities throughout the US, even on the commercial side, you're talking under 50% utilization of spectrum. So we can no longer afford to do that. And I really enjoyed the previous panel where they're talking about having, working together and having these conversations, because that's really the only way that we'll be able to get toward coming up with a more optimal solution.
Thank you.
Yeah.
Oh, go ahead, Pete.
Maybe from my side, the emphasizing what John was saying, that I like to adding a word operational, or sometimes in a technical community where we're putting a dynamic spectrum sharing. But I agree with Mariam also that there are many different ways to call it. The main danger is that whenever we are writing white papers or having our fights, especially in the policy domain, we are careful enough to define what we mean actually we are talking about, because the confusion which can come up if we don't have an agreement what we are talking about can be a huge. And one is definitely that when we have an engineers talking about operational spectrum sharing, there is a kind of highly different view when more policy people or regulators are talking about spectrum sharing policies. So in a perfect world, we would be agreeing our terminology and fix them, but then I'm a pessimist enough that I think there will be always a little bit of the loose ends, and we have to be careful on that. Adding maybe a little bit of the European way, that where I'm seeing in this side of the Atlantic problems is that partially because of the loose terminology, sometimes in Europe it's not even clear, even in a policy domain, that who actually has the power. Is it the European Union? Is it the nation states or the standardization bodies for making certain kind of sharing decisions? And it can become a very acronymous battle. And then in the end of the day, you fight 2 years and you find out that everybody was fighting on the different thing. So we have to be careful with the terminology.
Thank you all. Thank you so much. And just maybe one follow-up question on that. And then I want to move to another topic about scarcity. Petri, in our prep calls, one of the things you talked about, which really struck a chord with me, was you warned us of the dangers of placing complexity on complexity. And I thought that fit well with what you were just sharing about engineers talking about the operational aspects. I wondered if you cared to comment on that here.
Yes, I mean, my complexity comments are kind of in two domains in fact. So adding complexity over the complexity is, I think it generally, we have to be careful in operational spectrum sharing or even sharing policies. So there's almost inherent danger with us as an engineers for adding more and more things because it's a fun and it shows that we are intellectually very powerful. We are adding things, but once we increase a complexity, it's not only that we have a problem with increasing costs of the system, but more complex systems are also more fragile. And this, of course, comes if we consider, for example, the national security or DoD aspect. So we have to be careful that even if we are able to do some very smart things, if it increases complexity over the, let's say, an undefined boundary, we might have problems we would not like to have. And another problem, of course, purely in a technological area is that I have been starting to feel that the increasing talk about that we need an AI MLN because we have a so complex system. Is this just a hype, or is it a desperation that we are not anymore able to handle the engineering system we are developing? Because again, when it's a critical system, we actually would like to understand. We would not like to leave it for black box neural network decide whatever. But it goes again a little bit of this kind of cost and benefits and danger triangle, what we have to be careful for considering.
Thank you. I'll just give panelists a chance in case they want to comment on the comments there. I know we'll talk more about AI a little bit later, but anybody, or else I'll move on. Okay.
Just a quick comment.
Go ahead, Dr. Chapin.
Sorry, I should raise my hand. I think what Petri is talking about links to a common theme that we've heard from Scott Palo many times and from the others, which is the really critical importance of trust. If we're going to move forward in this space at all, the various stakeholders have to trust that their equities will be protected and that they'll be able to predict the return on investment depending on where you sit. And the more complexity we have, the harder it is to trust. And that's a really interesting challenge in order to move forward effectively. Thank you.
Jonathan, go ahead. Thank you, John.
Yeah, and another aspect, and I know you said we're going to get into the AI ML conversation a little bit more as it relates to spectrum sharing, but one concern that I have, and that we've seen, is that even if you were to get to pretty good solutions in terms of the optimality of sharing the spectrum with these techniques, there's a lack of traceability in terms of figuring out. So say there is an interference event between two parties sharing a certain spectrum band. It's difficult, again, with the black box neural network that Petri mentioned, to really trace back what caused that. So was it the system itself, disobeying some policy or rule set that was put in place? Was it a derived policy, that was pulled from a regulatory document? Was it a spectrum manager who's actually in charge of, allowing those systems to access that spectrum? So the provenance piece, being able to trace things back to their root, the source, lacks there. So really what is needed is more of a electromagnetic spectrum ontology, like an ontological framework where you have, that traceability aspect.
Thank you, Jonathan. And we are definitely coming back to identifiers as well. Maybe just before we do, just to finish setting the forum, thank you so much to all of you. And thank you, John Chapin, for making the comment about trust. I think now we've heard that in each panel, which is, and from the ambassador. So it's a great line throughout this. I want to get to asking all the panelists, how real is scarcity? And maybe just before I do, just to acknowledge, Marty Cooper recently published his autobiography, Cutting the Cord. And in it, he said, there has never in the history of radio been a scarcity of radio spectrum, and there will never need be a scarcity in the future. Since radio's invention, technologists have created new spectrum faster than uses for that spectrum has been intended. Technological advances in spectrum use and efficiency have continuously kept ahead of ever-rising demand. I guess I'm wondering how our panelists, how my great panelists feel about Marty's, you don't have to comment on Marty's comments specifically, but just mostly how real do you feel the scarcity is? And then we'll next get into some meaty, more technology issues.
Maybe I'll start for hopefully increasing the controversy in our panel. So in one sense, the scarcity is there. I mean, everybody has been seeing this, everything is allocated maps. So maybe in the policy domain, we have some issues. But if we consider pure physics, or let's say an engineering, I tend to be a little bit more in the Marty's camp. And it comes to the point that what we mean with the scarcity. The one way is to say that, so can we pack more systems? So let's forget the cost, we forget the business consideration. I don't think that we have a scarcity. Actually, the Marty itself has been sometimes showing a very beautiful map where he has been actually showing that almost all, I'm a little bit exaggerating, but almost all the extra area bandwidth, what we have been getting, is not coming for us to making a massive MIMO or better modulation. It has been coming from making a smaller and smaller cells. And obviously there are some physics limit how small cells we can make it, but we are very, very far away from how small cells we could generate. That doesn't mean that it would be economically possible, but you know, kind of fundamental sense. There's a lot of spectrum to be used, especially if we go then to millimeter wave bands or terahertz band, where we have a so narrow beam widths that we can really make geographical packing very strong. I think a more research question is that where is the boundary between economically viable engineering and availability of the spectrum? I'm still more in a, let's say, in a positive side as an engineer, that there's not really a spectrum scarcity. We still are getting wonderful new technologies coming in. You might then ask that why everybody speaks about scarcity. And this is maybe my controversial part, that I have not been seen too much, even an academic community pointing out that there are also reasons for claiming that there's a spectrum scarcity while there is no spectrum scarcity. And that's when we are talking about especially cellular operators. You have to remember that they have, in one sense, economical incentives to hog spectrum and keep new entrants out. So the whole point is that that's why I think we need more and more kind of very level field discussion and hopefully independent people looking the issue. It's not so easy than just listening to a couple of CTOs or CEOs telling that, please, we are lacking again a spectrum, we need more.
Mm-hmm. That's a very interesting answer, Petri. I see Mariam's raising her hand. Mariam, and in your answer, I know you're going to reply to Petri's good comment. I'm wondering if you could tie it in at all to David's comments in the prior panel, where he talked about a carrot and a stick approach of creating incentives. To me, some of what Petri's saying there about getting to smaller cells is a bit of is moving towards, it's capitalizing on an incentive in a sense of using the spectrum an operator has. I don't know, you answer however you'd like, but I'm wondering if your answer might tie that in. Mm-hmm.
Yeah, absolutely. Well, first of all, thank you, Petri, for bringing that controversial point up. That creates a very interesting discussion. I think that, and I'm going to put my, I used to be a mobile operator, so maybe I can just add some color to how at least, typically mobile operators view this, and how it's hard that they would create the scarcity, right? That argument is a tough one, and here's why. First of all, I think mobile operators typically look at spectrum needs based on their capacity forecasts, right? They do this years in advance, because if they were wait for the capacity crunch to come, it would be too late. So when they talk about, needing spectrum, it's way in advance due to these forecasts. Additionally, I think it's important to highlight that there are lead times involved from when spectrum's assigned to when it can be deployed for public use. So sometimes this may look like somebody's sitting on a spectrum, but ecosystem development, widespread deployment takes time. And the other aspect I think is important is that, if you look at traffic demand is not uniform, and it peaks during different hours at different locations. So, the aggregate demand when averaged over hours and days in geography looks low, that's for sure. But it's true that spectrum really is there to meet the peak hours and the population, okay? So in some cases, therefore, that spectrum is underutilized in other areas, but the point is that it needs to be more targeted. Now, when all of these things line up, sometimes, again, if everything lines up, you do get, an example of this year where there was an earlier auction this year on C-band, and you have an operator already deploying 7,000 to 8,000 C-band sites this year. But that's the little bit of the stars aligning with the development and things like that. So I just wanted to say, it's an interesting discussion, but I think just, from a mobile operator perspective, I'm not sure if they're trying to create scarcity. And Nomi, to the point about the small cells, I apologize that I missed the last panel. I didn't hear the point. So I'm gonna pass on commenting on that. So.
No problem at all. That was a great answer. Jonathan, do you want to comment on the scarcity?
Sure. I actually have, of course, tremendous respect for Marty, and I believe his technical point is well-founded. But I would say that whether or not there is scarcity from a technical point of view is sort of irrelevant to what we're dealing with here. And the reason is that there are long-established regulatory structures that make it difficult and expensive to launch a new service or expand a service. And there's long-established business structures that are assumed and maybe in some cases derive value from the fact that spectrum access is a barrier to entry. So we, by definition, have scarcity because of the system that we live in. And the conditions that create that are not going to change on timescales less than decades. Certainly at the NSF, we are investing in the fundamental research and the basic and applied understanding that can help to change that situation. But we really do need to make all of our short and medium term spectrum related decisions, understanding that scarcity is a reality.
Yeah, and I would agree with Dr. Chapin on that. I think it's not necessarily a scarcity issue. I mean, if you look at sub 6 gigahertz, there's plenty of congestion in the current regulatory structure. I'm just talking commercial side, similar on the federal and DoD side as well. But that congestion is really a byproduct of the regulatory structures that have been in place to regulate our spectrum for many, many years, and will likely continue that way. Now, it goes back to what I said earlier about, from a technical perspective, of course, you could come up with a more optimal solution to the optimization problem. That's not the hard part. What's the hard part is basically affecting material change in the way our spectrum is essentially managed and regulated. And that will allow for more innovative approaches in the utilization of that spectrum. We've heard about cognitive radio for many years now, like decades. There's been many compelling demonstrations over the years on, being able to maneuver through interference in a shared spectrum band with technology. It's really, in my opinion, it's a matter of catching the policy up with where the state of the art of the technology is. Of course, you have millimeter wave up to terahertz, as was mentioned. There's plenty of available spectrum up there. It's not really a scarcity issue.
Thank you so much. Those were fantastic answers. Thank you. Well, moving on now to like a bit more deeper into the technology. I'd love to talk a little bit about and hear everybody's thoughts on what we can learn from historic efforts to share spectrum. We've always had various systems for reusing the airwaves across frequency, space, and time. And it's also been nearly a decade since the PCAST issued influential reports declaring that the norm for spectrum should be sharing. And certainly we started with sharing with static regulatory separations and then moved to the coordinated sharing effort of the AWS-3 band. I would love, and we kind of sent around amongst our panelists a list of various developments. And I can ask you about them specifically, or I'll let you just speak to them. Would one of you care to start just to share your thoughts on one of the historical developments, be it AWS-3 or our largest real world experiment in spectrum sharing to date, the CBRS experiment?
Sure, I can share a little bit about maybe AWS-3. I think as a part of that, I mean, AWS-3 was a really good example of several things. I thought there's definitely, there was a concept of, again, talk about misuse of terms and confusing everyone but dynamic spectrum sharing, because that term gets coined in different ways. But in this way, it was dynamic sharing in the sense that basically, with respect at least to one of the sections where there were weather operations and actually uplink services with mobile, there was not only analysis done with coordination zones, but also sort of real-time systems. Something called an RFIMS was created over there that tried to accommodate more use of the spectrum through measurements. And so that was, an interesting first application. And basically it looked at, and what NOAA was doing particularly, and a few other agencies were looking at basically how this RFIM system looks at, sort of early deployments to later deployments and how they can balance this act. Because when you deploy mobile networks in a band that's newly allocated, you don't all of a sudden have 300 million users day one. You basically start with ramping up, and mobile users are transient. So I thought that was a very interesting learning that, if that gets, when that gets implemented, that we could look at some real-time measurements done by, sort of the RFIM system, and then in addition to some of the coordination zones that was created. So that, I think with CBRS, that's also another example of a dynamic sharing, where, there's the sensing, and basically there's also multiple licensees in the band. And I think there's definitely, the deployments are coming along. It was auctioned last year. And I think looking at that band and looking at the deployments in the future is going to give us a lot more learnings, again, as we ramp up, because no spectrum gets turned up day one all of a sudden together. So very, very good learnings over there also to look at as more deployments are made.
Thank you, Mariam. John?
Sure. Okay. Well, I'll answer the question by turning it backwards. I'm going to take some answers. I'm going to state some lessons that I think I've learned, and then maybe just give one example for each of the kind of historical sharing experience that it comes from. So 3 lessons. The first one is that having some form of ex post enforcement is really an absolutely necessary complement to the designed ex ante sharing mechanisms. One example that among several that supports that is what happened in the 5 gigahertz DFS band, where the very carefully designed sharing mechanisms ended up not working the way they were planned in the field, in part because of user action. It took quite a lot of effort to solve that, and we still have some ongoing interference issues as a result. The second lesson is that sensing-based approaches inherently limit both your spectral efficiency and the evolvability of the system over time. And really, information sharing between the spectrum users is critical. And so there we've seen this learning happening in the 3.5 gigahertz CBRS band, where there's a recognition that we need to evolve from the environmental sensing capability to some kind of incumbent informing capability. And the third lesson I would draw is that access level agreements are critical. That's a term I came up with. Maybe there's a better one floating around in the community, but by analogy to service level agreements in telecommunications, an access level agreement is something that specifies the quantitative thresholds that define when harmful interference occurs. And those may be time-based or power-based or something else. We really need that because dynamic spectrum sharing rests on having some form of automated or at least pre-specified spectrum management. And you have to have quantitative targets. We can't rely on the old approach of just sort of, I know it when I see it, harmful interference. So we've got multiple experiences, whether that's the TV white space or the 5 gigahertz DFS or the cross-border issues between the US and our neighboring countries, where we can see the importance of having these quantitative targets. Everybody can plan if they've got them. We also note that if the regulator has to establish those targets through a proceeding, it is a long and painful process. The 5 gigahertz DFS took 3 years of negotiations and still didn't get it right. So really the future has got to be access level agreements as contracts between the spectrum users themselves, and that everybody can agree to and then plan for in the future. So those are my 3 lessons. Thank you.
All right, so yeah, I can share some lessons learned from over the years. I'm glad you brought up the PCAST report. I encourage anyone who's interested in spectrum sharing to reference that document. I saw something in the chat about it's sort of like highways where we plan our road infrastructure for the maximum traffic, right? And if it's the middle of the night, maybe there's only cars would only really need to use one lane, but at peak times they would have to use all the lanes and then some. So spectrum does have some similarities. The Obama administration had drawn that exact analogy in the PCAST report. I believe Preston Marshall, who I think currently still works for Google, had been on that advisory board for the president. I bring him up because we worked on the WIN forum, which helped set the standards for the CBRS, Citizen Broadband Radio Service. Of course, that's 3.5 gigahertz, but spectrum sharing with Navy radar and commercial systems. So that's kind of a neat lesson learned for some current work we're doing, which is to basically come up with a spectrum coexistence and sharing system to allow for commercial 5G network that's being deployed at Hill Air Force Base. It's a standalone private 5G network, and Nokia is the prime on that, where they're deploying a network that will be manipulated by a spectrum coexistence and sharing system to be able to maneuver through incumbent interference presented by various DoD spectrum dependent systems. such as the airborne warning and control system or C13 station keeping equipment, et cetera. But I guess the one of the interesting things we've done, and I did this through the AWS3 bands experimentation as well. I was part of a committee called the Spectrum Sharing Test and Demonstration Steering Committee. Is actually led by the Defense Information Systems Agency. And as part of that, the NTIA was involved in ITS, which is based actually out your way, Mountain Time out near Boulder. It's the Institute for Telecommunications Sciences. They did several data collection measurement campaigns to really figure out what the thresholds would be for interference to allow for spectrum sharing between the commercial and the federal spectrum dependent systems. More recently, they've been helping us on a big program that we're working on, dealing with dynamic spectrum sharing and utilization between, again, commercial 5G and those various spectrum dependent systems on the DoD side. We've been doing flyovers and data collection measurement campaigns at Table Mountain, which is a radio quiet zone just north of Boulder, Colorado. So we're working with Frank Sanders and the team at ITS to really figure out what is needed to be able to effectively share the spectrum. The other thing too is worth bringing up is radar altimeters aboard both commercial and military aircraft. There's concern about how 5G will affect those globally. So we're also part of an effort called JIFRAG, which is the Joint Interagency 5G Radar Altimeter Interference Program. And I am not the lead for that one, but I do head up a sub-working group that's really looking to do flyovers and set up this 5G network to be able to do testing, collection, measurement campaigns to really figure out what is needed to be able to effectively coexist and what those harmful interference thresholds are.
Yeah, maybe from my side, the one thing I'll start from the trust point of view, that both in the US and European-based projects I have been involved in, especially if you have an actual operators or defense forces involved in, you get very rapidly in an issue of the trust, that what's going on. Okay, we share, but is everybody actually following the sharing rules? And this is now entering even with licensed spectrum access to commercial domain. So John was pointing out quite well that in order to have enough trust, you have some kind of ex post enforcement, to the point that you have to be able also to prove that something happened, that somebody is not crying wolf or whatever. So the related to this is that I think one of the surprises, if we think about especially the DSA community, is that everybody was first believing that we just make dynamic spectrum measurements and then we go to the white spaces. And I think we more or less have been proving that this is not an approach to go. But if I have to guess, we probably will have a renaissance on the spectrum measurements, not so maybe sensitive ones, but exactly for having enforcement, the provability that the spectrum is shared properly, because otherwise I don't think that we are able to build a trust, at least in some areas where there might be a local scarcity or local very, very high level sharing. The another thing which I think I have learned is that there's still a little bit some pockets, at least in an academic community, who are thinking that it's enough for defining a primary user, so to say, and then you have a spectrum sharing. But this is not obviously a case. Actually, you have to define who are the sharing entities, in a technological sense. because the whole point is that how quickly they can release spectrum again, what kind of aggregate interference they can generate, and indeed actually whether it is for the secondary users commercially viable to use shared spectrum depends very highly what kind of system you are putting there to share. So we should be careful to define all the sharing entities technologically. And the third, probably coming from all of my career, which starts somewhere around the second generation, is kind of piece of warning, which I would hope that the Mariam is especially agreeing, is that things tend to evolve differently than what we expect. So even if you are a cellular device manufacturer, of course you are doing lots of tests, you deploy test networks, you do things, but once the real heavy-duty commercial networks are there, people are starting to use it, you find it in a few years that, oh no, we didn't think about that, or we didn't think that the users could actually come this kind of applications. And a good example is that in the beginning of the 2G, nobody thought about that you would like to put the TCP IP traffic to the cellular network. You would have been laughed in the some research centers telling that we have to worry about data traffic, because everybody knew it's a voice traffic, find a peak time, dimension the network, done. And then people found that actually even a low bit rate data can be extremely valuable. So this is, of course, which is making this whole game very difficult, because we have to leave a little bit tolerance on our both regulation and the technology development for unknown unknowns, so to say. Things really, in my 30 years in this business, things tend to evolve completely differently what the best purposes bona fide planning is showing. But that's also, of course, the reason for increasing our capability for dynamic sharing and sharing systems, because that would give us a capability for evolve much more faster, because really the problem is that the regulation is too slow. The technology itself is not mainly a slowness, it's that if the services and everybody is fixed too tightly, then we start to have problems, kind of artificial scarcity problems.
Yeah, absolutely fantastic answers. Now let's move into the technologies, but if you want to come back to some of these historical examples as we're talking through some of the technologies, please feel free. I'd love to hear our panelists talk about some of the technologies that offer promise for inter-service sharing. I'd like to spend most of the rest of our time here, and I can ask you about specific ones, but I know I did send around a few from our preparatory discussion, so you could pick any of them and speak to their promise. And why don't we also fit certainly the discussion of AI fits here, but also I know we talked about this in the challenges section, but please feel free to also to comment here about the importance of requiring that all transmitters use a unique identifier. And if we don't get to that here, I'll call it out later, specifically later. But for now, yeah, I'd love if you maybe pick one of the technologies we talked about that offer promise and talk a little bit about how they might help in managing increasingly complex multidimensional interference environments, or our desire for inter-service sharing, which offers its own complexities. So if you could each maybe pick a technology and speak to it, that would be great.
Sure, I'll pick two if that's okay. One of them is AI/ML. I wanted to clarify that one a little bit more about what I mean, because I think it's different than what the context of AI/ML that was used earlier. And then the second one is, I think, convergence. And I saw someone in the Q&A talk about convergence, so I think it's important to talk about that as well. Let me just hit AI/ML first, but I think first of all, I mean, currently sharing is centered around developed technology. Okay, So instead, I think technology should be developed to embrace sharing. So I think we should think ahead this time. So just picking on 6G here, for example, for a second, they should consider how future aspects of how cognitive radios will use AI and ML technologies and deep neural networks, right? I mean, this is about the technology doing that. I'm not talking about AI ML to manage interference. That's not it. It's the technology itself actually, having cognitive abilities and using these things to be able to do many different ways of coexistence with other technologies and manage interference. So I think that it's an opportunity right now to look at this while future technologies are looked at. So, and I think it's important to incorporate, and would love to hear other thoughts on it. The second one I want to hit on is convergence also, because if we could talk about that, it's important because we have to talk about our future networks and how connectivity will evolve in the future. When we're talking about connectivity, we have wired and wireless networks, right? So right now there's new technology enablers that are creating a dynamic where we're getting an opportunity to converge multiple access schemes between wired and wireless technologies, right? And so once you do that, a couple of things happen that make it very interesting. First of all, just looking at the wireless side, through convergence, we can certainly bond different spectrum bands, including licensed and unlicensed. If a portion of spectrum becomes temporarily unavailable, operator can deliver the same user experience that's expected somewhere else, okay? So that's one thing that convergence brings. Convergence also allows multiple operators to provide a consistent and seamless user experience through their service boundaries via open standardized applications, APIs, and things like that. So that's an enabler too. I think that what happens is, whether through the use of common platforms or APIs or both, convergence promotes better interworking and information flow with various network elements. So that's a key ingredient for enabling effective spectrum sharing. So for example, one of the projects we're looking at CableLabs is something that allows traffic steering, splitting and bonding among various wireless networks using real-time network data to drive the optimal traffic management decisions. This could play a role also in sharing. So there's definitely an opportunity there, for convergence and using these new technologies.
Thank you. Thank you so much. That was a fantastic answer. Thank you. Those were very practical examples. Others?
I don't know if Jonathan is being quiet for the same reason I'm being quiet, but being at NSF, people write proposals to us all the time, and I really can't bias those by picking winners and saying certain technologies are more important than others. I would just highlight that NSF has a program running on technologies for promoting spectrum coexistence. It's called SWIFT. We've given 2 years of support out. If you type SWIFT into the NSF award search, you will find dozens of really interesting technologies that were judged worthy of pursuing, that fall into a bunch of different categories. And so I just really need to leave it at that. Thank you.
I understand.
Yeah, I'm in the same boat as Dr. Chapin, and that is the reason I was holding back. But I will say that there are a lot of key enabling technologies. I won't necessarily hone in on any just one, but I think it's inevitable that AI and ML will play a part in the future of spectrum sharing. I will point some folks to the DARPA Spectrum Collaboration Challenge, which was a program that actually did utilize AI and ML successfully to allow for on the management side. So the side. So I know the device side was also mentioned, which I agree that will most likely be in the future. But the thing to just bear in mind is that traceability aspect. I think there are other options. I think a whole electromagnetic spectrum ontology is really what's needed to be able to, when there's an interference event, to be able to trace back who was at fault, and that enforcement that was talked about earlier by several of my panelist colleagues, that would potentially enable them to be able to figure out, why something occurred and be able to follow up appropriately. I will say there's a lot of 5G enabling technologies, which are extremely interesting, several of which various vendors are utilizing on an active program under the 5G initiative led by the Office of the Undersecretary of Defense Research and Engineering Division. Essentially, you have everything what about like massive MIMO, right? So to be able to in a multi-user context, being able to steer the beams, essentially the electromagnetic energy in a direction so as to allow various users the bandwidth or essentially that they need to perform certain tasks. So it would be a different allocation, say for someone, but it'd be a different, you take in the spatial domain into account rather than just the frequency, right? So assuming they're in a shared frequency band, you could, someone streaming Netflix could get, a certain amount of coverage versus someone just checking an email or a text would get, a smaller allocation but essentially you're taking in not only the frequency part, but also the time and also the space. So you have all three dimensions, which isn't currently captured in the current regulatory structure.
John,
Yeah.
go ahead, Petri.
Yeah, maybe from my side, it's a difficult to pick any winners, but why it is so difficult is also that it depends whether you are interested in a short-term, mid-term, commercially viable, or let's say a foreseeable techno-economics, or then just dreaming some very academic, but not knowing whether you are able to do it or whether it's too expensive. But kind of low-hanging fruits, I would agree with Jonathan, is that generally everything in a massive MIMO or lately in academic research, there has been lots of talk about cell-free MIMO or cell-free massive MIMO. That's interesting. It's kind of related is of course using a millimeter wave bands, because there you definitely go with the phased antenna arrays with very, very narrow beams, which means that you have a huge spatial reuse. Now, all of these technologies, the one point is still that there's still lots of question marks. I could hype it as much as I want, but in all reality, trying to be honest, we still have even an academic question marks how well you can make various parts to work. But we get also to the point that what service you want to do it. And I think the millimeter wave is a good example, because I think that we are seeing a little bit of the hype curve going down. Because if we were believing all hype, we did solve all the spectrum scarcity for, let's say, for normal operator business. There's so much spectrum there that at least in the midterm, everything is solved, especially because they're spatially so well reused. But the point was, of course, that if you need to support high mobility or long link distances, then you have a problem. You actually still need these lower sub 6 gigahertz bands. So we are again in a situation that even in a technology picking, we have to a little bit think about that what service we want to do it. Very long term, we have to remember that where we would like to go is, of course, to having a more and more fiber. I mean, that's ultimately what we would like to have it. And we have to remember this when we are talking about 20 years, 30 years. That's where we still want to get, because fiber is also a good friend of 10T small cell wireless. So that in one sense, this might be a crazy, coming from the majorly a wireless researcher, killer technology is fiber. We just have to wait quite long to get it there, but we should not forget that. Then in an AI ML, I have to say that I probably started to look at just after being an examiner for the Joe Mitola's thesis, and that's about 2000, 2001. So I have been kind of 20 years getting enough hit with reality. So I have become a little bit skeptic. This is not to say that we should not research AI ML. I also believe that it has a place, but I don't think it's gonna be as big game changers as the people believe. But one area where I believe it is a game changer, I have to also say that I'm biased because that's one of my research areas, is indeed that it's less on a radio level or spectrum level. It's more like indeed a traffic shaping or moving traffic for the different frequencies or between fiber and the wireless. I think there the machine learning can really give us a huge gains. And there's two reasons for that. The time scale is such that we can learn. We really can learn, and we have a better understanding that why various machine learning algorithms are giving us results what they give. The second reason is that we have such a huge amount of data there to actually teach, even a very deep neural networks. I'm a little bit more skeptical how much the academics can do there. Well, we can do some things, but my eyes are more indeed in the places like a CableLabs, Google and such, because you need to have an operational network data. You really need to have a massive amount of raw operational network data. Otherwise, it's again, you are just making a toy models which don't prove anything. But what little I have had an access for operational data, I'm quite gung-ho that that's where the ML, at least in the short term, is gonna make a difference. Not for inventing a new modulation schemes or rapidly jumping between white spaces. It's a little bit higher in a protocol stack, and it's really hands of the operational companies.
Thank you. Fascinating answer. Mariam, were you going to say something, or do you want?
Yeah, no, I was going to just definitely violently agree with Petri here, because he's absolutely right. There's definitely challenges around AI and ML that need to be sorted out, and the data aspect of it and the data availability of it is one thing. You know, access to the data in order to be able to do this is one thing, and also the amount of data. Let's talk about how processor intensive this could get when we're talking about real-time dynamic spectrum sharing. So that also is something that is a challenge today. So definitely very future looking, and I'm definitely hoping that you know, as we evolve, that these challenges will be solved. But I think the time to think about it is right now. Because if we don't do that, you know, I mean, this again, these opportunities of these new developers will come and pass by us, and then it will be hard to change because there'll be commercial networks, right? There'll be live networks. There'll be in people's phones and homes and everywhere else, and then it becomes even more difficult.
Thank you. I really enjoyed all of those answers. You know, one of the things that we've kind of talked about, or at least like touched on a little bit, is trust, identification, enforcement. I was wondering if I could ask the panelists and any one of you to talk a little bit about those issues. And in particular, I know there's work being done that the NTIA asked SISMIC to how could the NTIA's and the FCC's equipment authorization rules be modified to require that all transmitters use a unique identifier, since that will be such an important part of enforcement. We're enforcement to also evolve as these technology solutions evolve. If you wouldn't mind just to talk a little bit about that both as a promising new development and possibly to touch on some of the barriers.
I'll try to go first to make it short because I would love to hear the other people's ideas. I was the chair of that co-chair of that subcommittee, and my partner in crime is missing, Brian Tremont. So actually the two of us really did put effort around, trying to really go across the industry and the various sort of entities to ask their view of unique identifiers. Okay, and it became a very interesting perspective. I'll share some highlights because there's definitely opportunities with unique identifiers. I'll share the challenges and then would love to hear others' perspective. One of them was privacy and security. I mean, that became a very big concern, that if you do put unique identifiers in every transmitter and every sort of what will that do to privacy and security? And the second one became a cost perspective on the cost of these things, especially when you're going to these low-cost IoT type solutions and things like that. What happens when you do that? So some of the challenges were there, but with lots of also good stuff in there. Would love to hear the other panelists' perspective.
Okay, I'll speak to this at a couple of levels. With regard to the cost of the UIDs, the cost becomes very difficult when you're transmitting them, say, in every packet header. But if they are transmitted probabilistically, and maybe that probability can be adjusted over time, then you might be able to deal with the cost. So if there was some mechanism where, if there's an interference problem in a given area or in a given band, then someone with authority can come in and turn up the dial on how much IDs happen temporarily in that place, in that band. And there you would have perhaps enough information to help find the source of the interference. So we should be looking at those kind of adaptive mechanisms instead of a one-size-fits-all mechanism. With regard to the privacy side, Pierre de Vries had a very interesting comment on this years ago, where he pointed out that even if it's a completely opaque license plate, a random 64-bit ID, just by correlating that information, say, to 2 or 3 places that a person visits in the course of their day, you can de-identify them, de-anonymize them very, very easily. So you need to use modern technologies like encrypted sequences so that someone can't correlate it over time without having the secret key that, again, they would need a warrant or some kind of appropriate authorization to get a hold of. So I think there are many, many dimensions to this problem of unique IDs. I just want to take a step onto the other problem that Nomi talked about, the broader question of enforcement. Let's say that we could figure out that it was a certain make and model of device that was causing an interference problem in a given band. What do we do then if there's thousands or millions of them out in operation? And I want to give a shout out to a paper that Bill Lair and I did many years ago now called Time Limited Leases that offers a solution to this. Let's turn the problem on its head. Let's say that every device that goes out into the market in one of these shared bands, after some period of time, like several months, will stop operating, will stop transmitting, unless it receives a key through some authorized channel that lets it keep going. So then, even if something is completely causing a huge problem, all you do is wait a little while. And even if you have no communication with those devices, they will stop transmitting. And that might be a way that we could give ourselves a little bit of a lever to stand on to keep the spectrum less polluted over time. Over.
Thank you. Thank you, John. Thank you, Mariam. You know what? I'm going to hold Petri and Jonathan for a second and just ask, because I guess I see we're getting nearing to the end, and I just want to make sure we fit in that. I understand we have CU student Taylor Hartley. I know she asked a question to the last panel, and you're on hand to ask a first question from the audience to our panel. Thank you.
All right, hello again. So question for this one, talking about AI and ML, that's super hot right now. All the companies want it. They want to incorporate it into their business model somehow. So that means there's going to be fewer and fewer data scientists and engineers to spread around. And that got me thinking about how 5G really hurt the spectrum community, and between misinformation and conspiracies. And so I wanted to know, is that reflective in your hiring pool? Have you seen like a loss of interest in wireless? I know space is probably boosting it back up, but I just want to know what that kind of looks like right now.
I'll try to answer, and thank you for your question. So in general, I'll tell you, there's definitely the hiring space is getting tougher and tougher because of just simply new technology, merging technology, virtualization, colliding of multiple domains together, right? And you mentioned 5G, which is an interesting one. Whether some of that was due to the misinformation that was spread with respect to, some radio waves being harmful or creating some other things in the industry, it could be, but that's being grouped up in the general, sort of challenge with finding folks that are ready for the next wave of technology and ready for some of the changes that we try to see or incorporate in the industry, given all the new enablers, right? I mean, we're right now, you're looking at a world where you're moving from having a radio traditionally built to pulling it apart, putting a lot of it in software and using just common hardware to do things, right? So those are bringing different expertise levels that are required to the table. You have to mix, sort of an RF engineer with somebody who understands the IT side. So that created a big challenge in the industry as well, with two worlds meeting each other. So really good question, but I'm not sure if I've seen statistics with respect to the misinformation.
If I could just jump in and say that the question about the workforce needed for growth in this area to future spectrum professionals, that's recognized as a major challenge by multiple entities within the federal government. And certainly we at NSF have made workforce development one of the four main thrusts within our Spectrum Innovation Initiative. And it was listed as a key part of the program solicitation that we put out earlier this year for a large center scale activity in spectrum. So I think the question about making sure there's enough workforce out there is really recognized as an important one. The big open question, which maybe folks in this entire conference can help with, is what does that future workforce need to look like? Where is the need? What types of skills are required? And I really do hope that the community can come together and provide input on that. Thank you.
Thank you. I'm just going to read a couple. There's two open questions. I think the others are common questions here. There's one from Prasant. Says, in what ways can we incorporate factors of protecting privacy and limiting the data collected about locations within the specification of technology? This is in context of the small cells and the increased spatial density of cells deployed by the operator. How do we account for the fact that the systems can increase the risk of surveillance at the cost of privacy of individuals? I know we spoke to this some, but would any panelists care to elaborate further on that point? I know we did cover it some, right? We did.
So I'll speak to it briefly. So make a point with the ultra densification and the small cells, getting to femto cells, etc. But I will say that one thing, having been familiar with 4G LTE and the evolution to 5G, I will say that in the 3GPP standards, And even within the ORAN Alliance, which is, the Open Radio Access Network Alliance, there have been provisions put into the standards to enhance security of, of your, bits and packets going over the network, as well as for the individual user. For instance, with 4G LTE, one reason the DoD really couldn't use it, because there's this concept of better buying 3.0, where the DoD would like to leverage the billions of dollars of commercial investment where possible, of course, but there wasn't the appropriate mail and cyber hardening. There wasn't required encryption of the IMSI channel, right? So the International Mobile Subscriber Identity. So then there's well documented, you Google it, you'll find, things called IMSI catchers. And for, $1,200 in a USRP, a graduate student could create one of these things that could spoof your, UE or your phone, essentially, to send, route its traffic through that device, therefore, stealing very private information that's linked to your IMSI. In the 5G standards, again, the further evolution of 3GPP, the third generation partnership project, you see provisions made for the end-to-end encryption of the GMSI channel. They call it the Global Mobile Subscriber Identity in that case. So I get what you're saying. There's more granularity with the, the ultra densification piece, but there are provisions in the standards being put forth to ensure a security on the personal level.
Thank you, Jonathan. Let's go to Darcy's question real quick. Hopefully it's okay to run just a few moments over, because then we'll have gotten to all the questions. If I can ask the panelists to look with me, but I'll just read it real quick. Darcy says she appreciates John Chapin's remark about considering an ex-post enforcement upfront in any spectrum sharing solution. She'd be interested in hearing a bit more about our thoughts on automated ex-post enforcement and any ongoing initiatives or emerging technical solutions focused on that part of the problem. Can I ask if any of the panelists would like to answer that?
Maybe I can start with the partial answer. So the one kind of, for certain kind of exposed enforcement is indeed if we are putting commonly used spectrum sensing devices around. This is still a relatively general term, that what they are sensing. Are they just sensing that what kind of modulation is going on there, or whether we have an IDs or whatever, but generally that could solve many problems. I think we have a lot of technological ideas how we could use a common spectrum sensing network for that. The bigger question is that who's gonna pay it and who is gonna operate it. So it's again more in an economical side, where it's a little bit harder to see that who should do it. There's lots of ideas that at least one could start to do on a test scale that. And I think that there's some economical or regulatory benefits on that, because I'm flagging up again actually the relatively old paper and suggestion from Pierre de Vries, which was saying that maybe we should not aim at 200% guarantees that there are no interference, but we should kind of put a risk limit. So we would go to probabilistic regulation. It's a wonderful idea. But if you go to that kind of probabilistic regulation, then we are immediately in an issue that how we enforce it, how we know that these probabilities are not getting too high. But that's something I would like to see a research community and of course the companies starting to look a little bit more at what kind of sensing capability we would need it, and can we make it economically viable. It probably would need to be some kind of public-private partnership to make it viable.
Thank you. Thank you. With that, I know we are out of time, and I think we kind of got to all the questions. There's 3 left here, which I think were more comments than questions. I'm thinking. So I want to thank my esteemed panelists and thank all of you for your incredible comments, and thank the audience as well for their questions. So thank you so much, everybody, and I'll turn things back over to Keith. Great.
Well, thank you. That was a great panel. That's it for today. I don't know about everybody else, but I